here you go, U50, figure it out, that kind of thing, right? That's awesome. I'm like, I mean, as a data scientist, this is a dream, right? I can just be lazy as I want to be, and I'll get an awesome model to come out, right? This is great. All right. Where does it fall down? It falls down when I have too many independent variables. Random forests aren't really going to help me if I'm getting into like the millions or billions of features, okay? Google kind of ad prediction, you're talking like 1 trillion observations on like 1 billion features, roughly speaking. It's really, really, really big, okay? The number of random forests I would need to build is like incomprehensible. It would easily fill up that empty bookshelf that doesn't have any books on it out there. Just really, really enormous. So for those problems, we need to do something slightly different that I'll talk about in a second. Random forests on Hadoop are actually pretty easy to do. A guy who works for me named Uri Laserson wrote a blog post about this a couple weeks ago about how to do random forests on Hadoop, especially using a wonderful tool called R, right, by doing some sampling tricks. Uri, it should go with, you know, I don't know why I'm mentioning this. I'm probably arguably inviting a sexual harassment lawsuit by bringing it up, is one of the 38, is number 38, is one of the sexiest scientists of 2012, right? It was like number 38. He's a very good looking boy. That was the moment when the lawsuit happened, in case you were keeping track. Along with that, there's a wonderful, wonderful trick we can do called the Poisson bootstrap. Poisson bootstrap. It is a way of creating multiple samples from a data set in parallel. One of the problems with like doing this random forest sampling is we have to like construct each of the samples by resampling from the data set. So you pull an observation out and then you like, got to throw it back in and like possibly resample it again, over and over and over again, right? And doing that in parallel can be kind of tricky. The Poisson bootstrap is this neat trick for like doing this in parallel over a single pass over the data. And if you're incredibly interested in this, and I mean really how could you not be, we wrote a wonderful blog post about it that I encourage you to go read, all right? For very, very large scale stuff, everyone, everywhere does essentially stochastic gradient descent on a logistic regression model. Logistic regression, and just in case you don't know, it runs your life. It is your credit score, it is ad models, it is everything, right? Logistic regression really kind of like runs the show. And what's great about these models is these are enormous models, but you can actually fit them on like a slide. This like could easily be on an index card, right? The whole equation is right there, the little like sort of theta j equals theta j, blah, blah, blah. Yeah, this is actually fantastic because it sort of turns into a systems problem at scale. It's not a math problem anymore. It's not a computer science problem. It's not a, not a modeling problem. It's a systems problem. How do I build a system, distributed system that can handle the volume and scale updates that I'm going to have to throw into this model in order for it to perform well? All right. Last but not least, all right, the third thing we can do, we can cluster stuff. K-means clustering, all right? A lot of my customers very excited about K-means clustering. Clustering in general, right? What's great, the great thing about clustering is I just give you a whole bunch of data and the K-means algorithm like takes a look at that data and says, all right, I'm gonna go find some structure. I'm gonna go find some subsets in that data. I don't have to do any work to label any data. It's really awesome for me, right? So a lot of companies when they're getting started with data science teams will say, okay, hey, let's do a clustering project. Let's come up with like some customer segmentation, okay? Let's get a whole bunch of customer data and we'll segment these customers into, segments. And we'll show it to the marketing department, okay? This is what's going to happen. They're going to create their clusters, bring it to the marketing department, present it to them. Two possible outcomes. Outcome number one, marketing department says, yeah, that's exactly how we think of our customers. Thank you for telling us something we already knew. Not very helpful. Outcome number two, no, that's not really how we think of our customers. You must have done something wrong. Go back and do it again. Until at which point you iterate until you converge onto response number one, right? It's really unfortunate. So the thing we don't use K-means clustering for is like the clustering. It's sort of funny. When I run K-means clustering, I actually don't care about the clusters. What I do care about the things that don't cluster well. That's really what I care about. I do the clustering so that I can find the weird stuff. And this is very common in, say, like network intrusion detection and fraud detection and that kind of stuff. Clustering will work great for, like, say, grab all the stuff that looks pretty normal and pretty similar to other things and just kind of shove that over there. And let me, like, kind of, like, drill down on the sort of the needles in the haystack, right? The stuff that doesn't really look like anything else. It doesn't really fit in, because that's probably something that's, like, interesting for me to look at, all right? My input is just going to be a whole bunch of vectors with normally distributed values. And again, much of the art of data science is figuring out how to come up with those vectors with normally distributed values. My output is a bunch of clusters. The parameter I have to choose, as you might suspect, in K-means clustering is the value of K. And that's the most commonly asked question about K-means clustering. What should K be? Right? Should K be 5? Should K be 10? How do I know which value of K is right? All right, we'll talk a little more about that in a second. And K-means clustering breaks down when my points aren't even like close to being normally distributed. Like I can't even squint and pretend they're normally distributed. It just totally doesn't work. All right? In which case I have to do things that are just, ooh, awful. Don't even want to talk about them. All right. K-means clustering on Hadoop. Historically, I'm not going to lie, it hasn't been great. Okay, it's been much like the data scientists have been trying to do K-means clustering on Hadoop for some time. And they've been having about as much success as this dude has here with the pizza and the hacksaw. So it doesn't really work very well. We're going to talk a little bit more about that in a second. Let's see what we can do to maybe fix that up a little bit. Machine learning design patterns. Almost every kind of important machine learning system in the world, important machine learning systems are much like important software systems. They are kind of a disaster. You know what I mean? Like sort of like Google's core ranking code, like the actual like code that does the ranking of like who should go where, awful, terrible. 10,000 line function, right? Just an awful nightmare. Google's ad auction. I mean, I worked on the thing, so I can assure you it's truly a disaster, right? Important software systems that are like really, really important, are disasters. The only pristine code in the world is like the unimportant code that no one cares about. And so the developers have nothing but free time to make their code like arbitrarily beautiful. Okay, this isn't like a hard truth for too many people here. This is just kind of the way it goes. Okay? All right. Machine learning design patterns. Much like sort of databases and NoSQL stores and search indices and all that kind of good stuff, we use all these different algorithms in conjunction with each other. Okay? If we're doing like a recommendation system, we probably really have like multiple machine learning algorithms behind the scenes. There's a collaborative filtering model, right, that's trying to like find signal and predict movies that you're going to like from your friends or from your previous behavior. There's also probably like what's called a content recommendation engine, which is just looking at your tastes and features of the movies you like. What kind of actors do you like? What style of movies do you like? And is doing much more of a classification model to try to predict what movies you're going to like. We have all these little like individual models that are all sort of working together as an ensemble to come up with like an overall prediction. And they have like little hacks and tweaks to them to make them like fit in different scenarios and all that kind of good stuff. And we end up with like a Rube Goldberg machine eventually. One of the things you kind of got to watch out for though, got to be like sort of careful about, is introducing dependencies between machine learning jobs, machine learning systems, okay? When the output of one system becomes the input to another system, like when I have like some sort of like feature extraction algorithm that's then like going to get fed into a classification model, something like that, that's where we end up in kind of a bad spot from an architecture perspective. Because now we can't really update model A without updating model B, right? Like model A can't get better unless model B gets better as well. And that sort of sucks, okay? There's a system like that at Google. It's like a very important machine learning system that feeds like 20 other machine learning systems. And it only gets updated like every couple of years. Because in order to like drop a new version of it, you have to like make sure that the new version works better like for all 17 different algorithms, right? Does that seem like a horrible nightmare, right? It's terrible, right? You gotta watch out for that. So we wanna kind of like, I don't know what the right software engineering word for this, because like, as I said, I'm a data scientist, not a software engineer. But it's like, we want these things to be mostly sort of independent of each other and mostly additive. We don't really want to introduce dependencies if we can like at all avoid it. Okay? So like, don't do that. All right. And then my last point here was just that as things get, like people talk a lot about real-time systems these days, right? Real-time this, real-time that. Real-time is an operational pain in the ass. Right? There are relatively few machine learning systems in the world that actually have to be real time. That is very much the exception, not the rule, right? The problem with real-time systems is not that like, you know, the system itself, like the distributed system can be pristine and gorgeous and beautiful. The problem is us. The problem is people. The problem is spammy data feeds. The problem is software bugs. The problem is this thing goes down or the machine learning model ends up in like some weird ass local optima, and no one really knows why. And no one can really understand the thing and figure it out. And this is not an academic problem. My first like month at Google, this is like one of my all-time favorite stories, right? The ad system started showing fewer ads. Like kind of like it was a progressive decline over a series of days. It's like number of ads being showed is falling off, right? And of course, Google has a bunch of knobs for tuning these things. So they just, like take the big knob. It's in Eric Schmidt's office. They just like turn the knob, and the number of ads goes back up, right? And it like works for like a day, and then boom, starts falling down again, right? They literally had no idea what was going on because they had built a system that was so amazingly complicated that no one could understand it anymore. There were so many different machine learning systems, so many different feedback loops that they like lost control of the ad system for a good month or so until they figured out like the interaction things that was causing the problem. And it's like, I was like super new to Google, right? So I asked like, you're new to Google and you get a mentor. I asked my mentor, a guy named Daniel Wright, Daniel, is it possible that the ad system has become self-aware? And that it doesn't like ads. All right. Okay, last but not least, something new. I give a lot of talks. I talk all the time. I'm amazing at it, what can I say? And I talk a lot, and people invite me to talk because I know a lot about this stuff because I've done it for a long time. But sort of one of the rubs of like talking about this stuff all the time is I don't really get to do it so much anymore. That sort of sucks. It's a terrible feeling, right? You know what I'm talking about? Some machine learning, kind of like manager types here, that kind of thing, right? It's just awful. It's the worst thing that can ever happen to you. So I've been trying to fix that for the past couple months. I've actually been like building something. And I'm introducing it here actually for the first time today. So, yay, exactly. I'm not gonna like do a demo or anything, I'm not that stupid. But I am introducing something new today. I'm kind of excited. All right. I mentioned K-means clustering on Hadoop, right? A lot of people have been trying to do K-means clustering on Hadoop, and it's been terrible. It's been terrible for a long time. Why is it terrible? The sort of core, so K-means is a heuristic. K-means is a trick. The actual K-means problem itself is an NP-hard problem, and the kind of common K-means algorithm, it's called Lloyd's algorithm, is an approximation to it, all right? The problem with it, though, two really big problems with it. One, in the worst case, Lloyd's algorithm is super polynomial in the size of the input. Cringe, right? People here are not software engineers. Super polynomial, really bad. Takes a long time to run. Super polynomial in the size of the input. Also, when it does converge, it can also converge to an arbitrarily bad solution, right? So imagine this is a computer science problem where you can wait an arbitrarily long time to receive an arbitrarily bad answer. This is not very appealing, okay? So this is sort of the state of K-means clustering on Hadoop. Lots of people have been trying it. It doesn't really work very well. Good news, I rag on them a lot, because I mean, obviously I hate academics. But they have come through for us in the past year. They have done something useful. I was at NIPS 2011, and one of the papers I'm going to talk about was introduced there, and it was like a beacon in a sea of like just useless crap. It was like the one thing, it was like, oh my God, someone did something useful. This is incredible. It's like so exciting. You guys can't really appreciate it. The trick, it turns out, is sampling. And I feel like with all this sort of like hype around big data, like sampling gets a kind of a bad rap these days. Like, people are like, I'm not going to sample anything. Like sampling, that's for suckers, right? Sampling is actually awesome. I'm like going to be the first one here to say that. I'm saying that as a Hadoop vendor. Sampling is amazing. It's really important that we record me saying that. No, I feel like a lot of the trick of data science is finding just the right way to take your big data set and shrink it down to small data. That is the art of what we do, is finding just the right way to do that. And the fact that doing that is hard means we have to like try it like a couple hundred times, which is, like thank God we have Hadoop for helping us with that. So I kind of saved it right there. But anyway, but like really what we're doing is sampling. So a couple of different options here. There's a project called Mahout. It's also called Mahout. It depends on what part of India you're from, what the right pronunciation is, so like don't worry about it. It's called Streaming K-means, and it's based on a paper by Schindler and Meyerson at NIPS 2011. I know you watch this and you've been drinking beer all night, and you're like, oh my God, I really have to go to the bathroom. Anyway, I totally did this to be mean. So Streaming K-means is a single pass algorithm for computing an approximation to like a good K-means clustering, like over the data. It's actually really, really cool. Very computationally intensive, but it does a single pass of the data and comes up with like a reasonably good, guaranteed approximation to the optimal clustering, which is fantastic, right? This is glorious news. So the Mahout guys are working on this. It's Mahout 1154. It'll be in the next release of Mahout. It's very exciting. The other one that came out, this is by a guy named Baman Bamani out of Stanford, super smart guy. You haven't heard of him yet, but you will soon. It's called Scalable Kmeans++. Scalable Kmeans++. And it essentially is the same kind of thing. You do a fixed number of passes over the data, like about 5 or so, and it comes up with a very, very good sample, a very, very good sketch of your underlying data set that sort of like captures the structure of the data and allows you to work like locally in memory on that sketch to come up with a guaranteed good clustering of your data. All right, so very, very good, smart sampling techniques. We're trying to stay away from like dumb sampling, like random sampling, right? Just grab stuff randomly because we don't know what else to do. That's stupid. We don't want to do that, right? We want to do smart sampling. Smart sampling, sampling that captures like the structure of our data and lets us make good decisions from the samples we create. All right. So, this is Cloudera /ML, which I realized kind of as soon as I named it was a sort of a terrible name. Because ML sort of suggests machine learning. And while it does that, it does a lot of other things too. It includes the implementation of Scalable Kmeans++. But it also includes a bunch of other stuff for doing sort of crazy things that you would think would be in like Hadoop but are actually not, related to like taking in a CSV file and turning it into a set of vectors automatically.